So our second skill in our 8th learning unit here on electron configuration and chemical periodicity is thinking about periodic trends. So this video is going to be much shorter than the one that we had on figuring out electron configuration. There's so much more to sort of think about that in terms of quantum numbers, electron configuration, atomic orbital diagrams, and all of that. So this one's going to be a little bit of a departure from that. Basically, we're going to be looking at how the periodic table is organized and thinking about several properties of atoms and ions and how they relate to where things are in the periodic table. So thinking about the periodic table, just to start with, this is Dmitry Mendeleev, and he is the author of the modern day periodic table. So here is just kind of some interesting excerpts from his notebook, just kind of showing what he was observing in terms of trends of chemical properties. So that's how the original periodic table was set up, is basically it was arranged in order of atomic mass, and then things that were in the same column represented things that had similar chemical properties from what was observed. And so this was a long time ago, 1870. Not too much has changed since then. This again was arranged in order of increasing atomic mass. But one of the things that we now realize with our modern day periodic table is that the increase that we have has to be because of increasing atomic number. So just the number of protons, remembering that atomic mass is protons plus neutrons, but because the number of neutrons can be a bit variable, it wasn't correct to actually just look at atomic mass. So again, our modern day periodic table, we talk about it being our best cheat sheet. Again, this periodic table will be always available for you to utilize as you go through and answer questions. So the trends that we're going to look at have to do with sort of connecting the columns and rows that we have on the periodic table. So this sort of last skill here provides a connection between quantum mechanics and then what we see in terms of chemical periodicity, which has to do with the electrons that we have in these outer shells. So we've mentioned these terms already, but just to kind of review them, sublevels are filled in order of increasing energy. So we talked about kind of filling orbitals in terms of their energy level. And that leads to electron configurations in outer shells that recur periodically. So again, that's how we get this periodicity, this repeating trend of certain elements that have similar chemical properties, and that has to do with the number of electrons that they're going to have in their outer electron shells. And so we define these outer electrons as valence electrons. Okay, inner or core electrons, if we think about sort of this being like onions and we've got layers in an onion, those ones that are buried in the core, we're really not going to be doing much chemical reactivity with those. The outer electrons are going to be ones that are in these highest energy levels, so that principal quantum number in that outer level. And even beyond that, valence electrons are going to be those electrons that are involved in forming compounds. So for most of our main group elements, the valence electrons are going to be the ones that are on the outer shell. But when we get into transition elements, remember those transition elements are that D block that we find in the middle of the periodic table. Those valence electrons are going to be not only the outer electrons that are in the S orbital, but the ones that are in the D orbital as well. So we'll get to some of that a little bit later on. So trends. We're going to talk about 5 different trends that we're going to talk about here. You do need to sort of know the trend and how it operates. So I'm going to tell a story with each of these, and hopefully when you have a story, it kind of helps to make sense. So the trend that we see in terms of increasing size or trends in atomic size, that size increases as you go from right to left and increases as you go down. So these are going to be the largest atoms down here, the smallest atoms up here. And so again, the story that we're going to tell is this Y piece. And the reason I tell you the Y is that it can be easy to get some of these trends backwards. So if we remember why that trend happens, then we don't need to remember what that trend is. So again, as you go across the periodic table, as we think about going from left to right, atoms become smaller. So if this is increase in size, obviously this is decrease in size. So why do things become smaller as you go towards this upper corner? And that's because there's a greater number of protons that we have in that nucleus, and they're going to be attracting and pulling the electrons closer. Remember, there's an inherent attraction between the protons, which are positively charged in the nucleus, and the electrons that are floating around outside. They're inherently attracted to one another. And the more positive charge that we put in this nucleus, the more they're going to pull those electrons in, and we're going to shrink that outer onion layer in so that it's smaller. So if you remember that, that's going to help you remember the trend in atomic size. Moving down the periodic table, when we add another onion layer, that's just going to make it bigger. That makes sense, right? So we're going to, if you want to think about it decreasing in size as we're pulling that onion and shrinking it in smaller as we put more protons in the nucleus, we're going to get bigger as we add another layer to our onion shell. So that's a way to remember atomic size. One of the things that we'll highlight here is that transition metals are less trendy. They don't tend to have kind of some rules to follow, so those ones are a little bit more unique. We're largely going to be comparing nonmetals to other nonmetals and then metals to other metals. All right, we also want to be able to think about what happens when you take an atom and you make it into an ion. So again, the trends that we see here have to do with the proton and electron ratio. So as we make something into a cation, what we're really doing is we're having a greater number of protons than we do electrons. So we're going to make cations be smaller because we're actually increasing that attractiveness between the positive nucleus and then the negative with the electrons. But we also have sort of another situation here to think about, is that when we take, for example, sodium and we take that one electron off, we're actually removing that outer onion layer because it becomes just like fluorine. We say that it would be isoelectronic. See if this makes sense. When we have fluorine, fluorine's in that group 7 that's going to gain 1 electron. So if we compare fluorine to fluoride, fluorine actually becomes bigger because there's now more negative than there is positive. So it's going to make our onion get a little bit bigger. But if we have sodium here, sodium as a metal versus sodium as a cation, once we lose that outer shell electron, we actually become significantly smaller because we've lost that outer onion layer, and now we have more positive than negative. They're going to be pulling those electrons in more tightly. Again, a little bit of a trap here. Don't fall into the trap that if it's on a lower row, since again, if you remove an electron, you don't live in that row. So that has to do with thinking about sodium here. When we remove that one valence electron in the outer shell, we no longer live in row 3. Now we only have electrons that live in row 2. So I have a principal quantum number of 2. Okay. Again, trend here, cations tend to get smaller, anions tend to get bigger. To remember this, just remember it all has to do with this proton to electron ratio. Again, when we have more electrons than protons, we can kind of expand out. When we have more protons than electrons, we're going to pull in, contract in. All right, we're going to talk about 2 things here. Ionization energy, which we abbreviate IE, and then electron affinity. So sort of a way to think about these, if you want to think about what ionization energy is, that's how easy is it to remove an electron? How much do you want to be a cation? Large ionization energies means it's hard to remove an electron. This guy doesn't want to be a cation. So if we think about things here, things that are over on the non-metal side, right, those like to be anions. So when you want to think about how much you want to be a cation, not so much. So these are going to have large ionization energy. So we can see this trend increases as you go from right to left. It also increases as you go up. It's actually much easier to take an electron away from a metal that's kind of low here on the periodic table because that electron's not being held very tightly. So it's much easier to remove it and make it a cation. So again, this trends with size. Again, think about if we're removing an electron, we're removing it from that attractive force that it's feeling with that those protons in the nucleus. So the further away that electron is, the easier it is to remove it. Okay, so we can see some trends here. We're going to map this onto several of the next pictures. We can think about reactive nonmetals are going to have low ionization energies. They're going to remove electrons easily. These guys like to be cations. We know that, right? Anions, nonmetals making anions, don't like to be cations. So they're going to have fairly high ionization energies. They're not going to lose electrons very easily. And then just remembering noble gases, they have very high ionization energies. They're really happy with the number of electrons that they have. So those are fairly unreactive. Electron affinity. So if ionization energy asks the question, how much do you want to be a cation? Electron affinity means, well, how easy is it to accept an electron? So how much do you want to be an anion? So what's interesting with this is these tend to be exothermic. Because you've got that positively charged nucleus, throwing another electron in there isn't necessarily all that problematic because there's an inherent attraction there. But two things, it does tend to be fairly irregular. And there are some cases where it actually will be unfavorable. It'll be endothermic. Okay, so again, adding an electron is generally a favorable or exothermic process because there's these attractions with the atom's nucleus. So what we tend to see is the things that really like to gain electrons are our nonmetals and become anions. They're going to have large exothermic activation energies. They want to gain electrons easily. They want to be anions. However, things that are metals, we typically think of those being cations. So they're going to have small electron affinities. They don't like to be anions, but they're still going to be favorable. They're still going to be exothermic. Noble gases here, just like we saw in the previous slide, they don't really like to do any reacting at all. So these are endothermic. They refuse to be an anion. They're unreactive. They don't want to gain electrons. They don't want to lose electrons. So they have energies that correspondingly reflect that. All right, the last piece to sort of talk about here is trends in what we call ZF, which is the effect of nuclear charge. So thinking about this, how much do the protons in the nucleus pull on the electrons, right? And it sort of trends with size again, because the closer those electrons are to the nucleus, the more they can feel it, the more that effect of that nuclear charge, the charge that's in the nucleus, is going to be felt. So the closer electrons are to the nucleus, the smaller the atom is, the greater that effect of nuclear charge is going to be. So this trends with size. The smallest are going to have the greatest effective charge, and then the largest and most metal are going to have the smallest effective nuclear charge. So impacts, right? This trends with both ionization energy and electron affinity. Attractions of the electrons for a positive nucleus are what really impact the energy required to remove an electron, and then the tendency of electrons to be attracted to the nucleus. So all of these kind of relate to one another. But again, think about these stories between the nucleus being positive, electrons being negative. They are attracted towards one another. So adding electrons is going to be favorable. Removing them is going to be dependent on how much of an attraction we feel between that electron and the positively charged nucleus. All right, so why is this important? What kinds of questions am I going to ask you? These are going to be another kind of series of questions where you might be asked to rank things. You might be asked to pick one out of a series of a group of atoms or ions in terms of which has the greatest or which has the least. Okay, so a lot of ranking type questions here. So with these ranking type questions, always ask the question, what's different? And I'm going to just go through a couple of examples here to show you the kinds of things you're likely to see and then the kinds of questions I tend to avoid. So I love apples to apples comparisons. So what does that mean? Well, I might ask you about species that are in the same row or the same column. I'd sort of classify this as the easy sort of answer. You're going to apply the trend rule as written. So what you might have here, for example, I might give you the halogen series, fluorine, chlorine, and bromine, right? All you're doing is comparing the trend as you go down a column. Or I might give you nitrogen, oxygen, and fluorine. I might give you something as you go across a column. So I consider those to sort of be the easiest. You're comparing something directly and you'll be able to more easily apply a trend. Apples to oranges are a little bit more challenging, but what makes these a little bit easier to think about is we're going to have two trends that kind of trend in the same direction. So for example, if we're thinking about size, right? If I were to give you fluorine and then sulfur, what you might say is, well, fluorine is going to be biggest or smallest because it's further to the right, and then it's also going to be the smallest because it's got the smallest n number. It's on the smallest row. Okay, so again, we know that going up and over is going to make us be the smallest. Something that I tend to avoid, but I'm going to show you an example here that I still think is a fair question, is I call these apples to rocks. It's like comparing two things that are really hard to compare, right? Two competing trends, right? Rather than being two complementary trends that might trend in the same direction, these are going to be competing trends. So unless it's something that I think is obvious, I'm not going to probably ask that. For example, what about oxygen and chlorine? Well, oxygen's further to the left than chlorine is, so that would make it bigger, but chlorine is further down, so that would make it bigger. So you sort of have competing trends there. But one trend I'm going to highlight here, particularly as it relates to size, is when you jump down a row in the periodic table, that is more significant than if you go to the left on the periodic table in terms of becoming bigger. So in general, jumping down a row is going to have a greater effect than moving within a row. All right, so that's our concept on periodic trends. Lots of qualitative questions you're going to see with that, nothing quantitative.